Okay, so we're going to talk about the physics of creating um, radiation or X-radiation or X-rays inside the tube head of an X-ray machine. The objectives that we're going to go over are we're going to define some basic terms. I keep looking here like it's up here, but it's not up there. It's right here. So we're going to define some basic terms associated with the physics, the kind of whole process that we're going to be explaining this morning. We're just going to very, very briefly and elementary review what the pieces of an atom, the parts of an atom, what makes up an atom. Um, and then we're going to describe ionization very briefly. We talk more about that a little bit later, but we're just going to kind of define the term ionization. We want to list the characteristics of electromagnetic radiation. That's really summarized nicely at the end of the PowerPoint, kind of revisit these characteristics. But in between, we talk about wavelength and frequency, and those are also parts of it too. And then the properties of radiation, again, it's really nicely summarized at the very end in some nice, concise phrases that are easy to kind of remember. Identify the component parts of the X-ray machine. We're going to try and look at that and get that in our head first before we talk about what those parts do to generate the X-rays. And then label the parts of the tube head. So I have a diagram here that we're not going to follow. If I could, I want to wait until hopefully the projectors are up because I want to have you follow along on the dot cam. But we're going to use this diagram, but kind of slightly different because I want you to hone in on some parts that the lines aren't necessarily going to. But that'll help us kind of hone in on the parts that generate the X-rays that we're trying to learn about today. Describe in detail how dental X-rays are produced. So this whole process you're going to want to memorize. Try to break it down into these really easy bite-sized chunks, and just kind of simplify it. But you're going to want to memorize it because gobs of test questions on the exam on week 5 are based off of the process. So it's really important that you be able to tell somebody about how X-rays are generated. So it's a great way to study is to teach a peer, teach your husband, teach your girlfriend, teach your kids, and just say, I know you don't care about radiology, but listen, I'm going to tell you about how X-rays are made. And then if you can tell them, then that's a great study tool. Describe in detail, I think I said that, list and describe the possible interactions of X-rays with matter. So we'll talk a little bit about that, and then we go into that more in the biology unit. And then discuss the difference between Bremsstrahlung and characteristics. So again, those are pretty simple, just definitions. I have an animation embedded in the PowerPoint that you can kind of visually look at it. But you just need to kind of give a 2-sentence maybe description of what's the difference between the two and what's occurring. Okay, I am going to skip my fun little, if you go to the next slide and you see a QR code, I'm gonna skip it because I can't pull up, but let me just ask you, when you guys think of an atom, what are some of the parts of the atom that you remember from high school or prerequisites? The nucleus, protons, neutrons, electrons. Anything else? Yes, that's exactly an atom makes up matter. It's a unit of matter. Um, so if you go to the next slide, oh, see, I hate this. I want my projector. If you go to the next slide, what do you already know about the atom? So we know it's the fundamental unit of matter. And the biggest thing that we're going to focus in on when it comes to an atom are the electrons. So it's nice to know those parts. Electrons are negative, protons are positive, neutrons are neutral, and that an atom likes to live in this harmonious state where everything's balanced. So if you think about it's like a mini solar system, right? All of these electrons are orbiting around the nucleus. So it's like a mini solar system in our like microscopic, made up of everything that's hard. So all of these electrons orbiting around the nucleus, and there's a certain amount of electrons that make up, do you remember the term valence or the orbit? They make up those rings. So there's a certain amount in each one. And the process of creating X radiation is manipulating and doing funky things with those electrons. So that's pretty much what we focus on is just the electrons. So that's about as deep as we'll get into that. I put a lot of notes in, you might notice some PowerPoints more than others. I put a lot of notes in the PowerPoints and I just try to like, if I don't say it nicely in front of you, I hope I've written it clearly. And so maybe between the two and then between the textbook, those concepts will become clearer. Um, Okay, so the next slide, slide 5, just some vocabulary. We already basically talked about this. Element, one type of atom, so it's not a mix of stuff, it's just one thing. And that's important when we think about the metals that make up the inside of the tube head, because we're talking about tungsten. It's an element, a precious metal, and it's a rare earth metal. And so we're talking about all of that coil that we'll refer to in a minute is all made up of just tungsten atoms. So it's the element, it's all one kind of atom. Atoms are a unit of matter, so we're zooming down into just those microscopic individual units. Then we talked about the makeup, nucleus, electrons, protons, neutrons. Atomic number is the number of the protons and the neutrons. I don't really visit that. The book talks about it because the atomic number correlates with ultimately like the density of the matter and which affects like how X-rays are absorbed. If something is dense, X-rays are just going to sort of be absorbed into it. If something is less dense and soft and gushy, X-rays go through it and they're not as absorbed as easily. So that's like the basic concept for the atomic number. And the book talks about it a little bit, but I don't really spend much time on that. We do talk about how matter affects X-rays, though, but not really specifically related to the atomic number. Ionization is just the production of ions, and we go into that a little bit differently. But basically, when we manipulate those electrons and an electron flies out of a valence, then the whole atom and the electron are now either positively and negatively charged instead of being neutral. And so that's what happens in ionization, and we'll talk a little bit more about that in another unit too. Binding energy, the electrons are bound stronger and stronger as they are closer to the nucleus. So those valences that are on the outside, the very outside rings, hold those electrons less strong or weaker than as they move in closer to the nucleus. Those are bound much stronger. And so when those get dislodged, we get varying powers of radiation. So that has to do with the power, like if it's a weak or a strong X-ray coming out of the machine.
When you refer to those sides, do you mean the way the X-ray looks, like it's either darker or lighter?
Well, it can affect the way it looks, dark and light for sure, but we'll stay in the place of the actual, before we talk about its effects on the picture, which is ultimately, yes, what it would, but we'll stay in the realm of if the actual photon, the actual X-ray photon that gets created, if it's a very high powerful one, meaning it just bombs through stuff really well, it penetrates really well, or if it's kind of a weak energy one and kind of either bounces off something or gets absorbed really easily. So that's what we're talking about it being, and it has to do with the wavelength and the frequency, and we'll get to explain that a little bit more, but that's a great question because ultimately, yes, it does affect the way an X-ray looks. Okay, so slide 6, each shell has a maximum number of electrons it can hold. So I kind of already said that already. And that's just kind of some basic. And the main shells that we're going to refer to is that inner shell, K, That's one that we talk about a lot. And then we also talk about outer shells. So you're not going to have to like memorize a lot of shell letters and the number of electrons that they hold, but K should kind of stick in your brain because specifically that shell with the orbiting electrons will be related to specific kind of radiation and scatter that we talk about. So that's really the only one that you're really going to have to kind of remember the K shell. But in general, we sort of talk about outer shells and inner shells and if the binding is weak or strong. Okay, so the next one, nobody's here to fix the projector. So take one, pass it along, and I don't know how to divide. I think there's one more. Take one, pass it along, and let's get familiar with the inside of the tube head. And I know there is a image that's similar but different that you're probably looking at on slide 7. So I don't want that to be confusing because we're actually going to look at two different, they're actually kind of two different parts that are in that picture on the PowerPoint. I hope I printed off an extra for myself. If not, I might go make a copy. But once they go around, if there's an extra one, just let me know. Did you guys sleep well last night?
Yes.
Yes.
I'm very much so.
Were you exhausted? Crashing and burning. I mean, I don't need to absorb nearly what you have to, but I was pooped. So I'm like, if I'm pooped, they are exhausted. It was a long day. I had to teach in the morning too, so it's just a lot of talking. Normally, none of us talk that much. Although radiology is a lot of talking because I have the double labs, so I have to repeat. Any extras at all? Did I print just 32? Okay, well, maybe I can just be okay. Okay, so when you look at the image on slide 7, what you're actually looking at is that outer part, that outer casing. That is what you like look at and hold and move. So that is an outer casing that is actually like, what do they call it here? The outside metal casing. That's not in the picture that I just handed around to you. What I handed around to you is just the glass tube that's inside of that metal casing. So that's what you have in front of you. So if you if you try to match up what you're looking at on the PowerPoint, it might get a little bit hairy-carry. So what I want you to focus on in relation to what we're about to learn right now is I want you to notice the negative and the positive. So on the negative side, you have kind of like a curved thing, and then you have a squiggly coil. And on that side is where it looks like the electrons are being generated. So the thing that's kind of a curved piece, the purple curved piece, somehow make a label that you look at and have it say focusing cup. That's the focusing cup. And the other, I should probably actually, before that, when you look at that image, if you divide the picture in half, the blue piece on one side and then everything else kind of on the other, on the side with the focusing cup at the top, write cathode. That's the cathode side, and it's the negative side. So put negative somewhere and put cathode. And that's the side with the focusing cup that I just had you label. Cathode is always going to be negative. The electrons are always generated on that side. And so those are some big points that you're going to want to remember. Okay, inside, sort of nestled inside of that focusing cup, that coil, that looks like a spring. That is the tungsten filament. Tungsten is a metal. So it's a filament, just like in a incandescent light bulb that they used to use before LED was the only thing you could get. It's a filament and it heats up and produces ultimately the electrons we need, but it's made out of tungsten, which is able to get really, 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 really hot. So on that side, we have our focusing cup, we have the tungsten filament, and then this is also that E and then the arrow. That's where we're gonna generate all the electrons that we need. On the other side, and I won't talk too much about the process, I just want you to visualize the pieces because we're gonna get into the process here in a second. But on the other side, where the blue piece is, at the top or somewhere around that right anode, 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 and that is the positive side. And the blue big metal thing is made of copper. I know you can't tell it's metal. I just said it was metal, but the blue part in that picture is a copper stem. So you could write copper stem. And it has a purpose specifically, and we'll revisit it, but I'll just tell you because I always jump ahead. It's just to absorb heat. So copper absorbs heat really well. And so that big chunk of blue is a copper stem. Embedded in the copper stem, all the way at the end, that little rectangle that's embedded at the end that's slanted, that's the tungsten target. So again, it's made out of tungsten metal, and it's the target. It's what the focusing cup is trying to get all those electrons to fly over and hit to generate X-rays. Oh, sorry, go ahead.
Before the blue part.
Okay, so yeah, so on this, yeah, so we have, and how'd you get that negative? And this whole thing is the copper stem. So this is the copper stem. Well, and see, I just would ignore what they're pointing to. I just make your own. In general, I'd rather you guys ignore all their numbers and lines and just we're gonna create our own. But yeah, this whole thing, so you can scribble out this team.
This whole thing, yeah.
Yeah, the way it's light and dark, I'm not.
I think so. Yeah.
The anodes.
Yeah.
Yeah.
Just to clarify, the first part of the blue part is the copper stem, just this part.
So I am not, so I do see on your picture how the blue is like two tones. I don't pay attention to that. Don't worry about that. Just the whole blue, whether it's light or dark, is the copper stem.
It's just the end is the tungsten target.
And then this right here. So I apologize. That's why I need a projector. Gosh darn it. So do you see the little rectangle that's embedded in that slanted end where it looks like stuff is flying out? That's the tungsten target. So if anyone needs to adjust, and if you want a new one of these, I am more than happy to print you out another one, just so that you can. I would like to have one that was just blank.
May I have
Have
a
lines on it. Would you like that?
Yes.
Yes, I can get you one at the end of class.
Thank
Or on break. So yeah, so that's where, okay, so what else do I want you guys to know? So the big things before we go into the process: focusing cup, tungsten filament, the copper stem, tungsten target, and then the whole thing, the encasement, that's actually leaded glass. So it's a glass tube. If you take it out of the X-ray machine and you go, what does this thing look like? It looks like glass, but it's leaded. So X-rays can't go through it because the lead absorbs it. So if you have this whole kind of gray outline, that's just leaded glass.
You can say like that is that.
Leaded glass tube.
Tube or cake.
Either way, I'm not gonna get too picky as long as I know what you're referring to. Down at the bottom where you see the red kind of streaming out of it, that is a window that's unleaded because there has to be somewhere for the x-rays to get out. So in this glass tube, there is like one little section that is unleaded glass. And that's where that red stream is coming out toward the bottom of the picture. That's where they exit the glass tube. Now, just for your further knowledge, just so you kind of get a better understanding of what you're moving around in that room, that little glass tube that we're describing right now sits inside of a bigger metal box, and it's filled with oil, packed full with oil. And so what you're moving around is basically like a big thing of oil with this glass tube inside. And the oil helps to absorb heat. Most everything that is produced in this whole combustion is heat and a little bit of x-rays. And so that's why there's the copper stem and then this thing that you're moving around that is filled with oil. It's all to just insulate and absorb the heat. So just so that you know, like the thing that you're actually like moving and putting up to a patient's face, that is, it's not like one big glass tube inside. It's like a little glass tube inside, and then it's like filled with oil. Yeah.
So the unleaded tube is a tube that releases rays?
Yeah, so the whole glass, it's maybe this, I don't know, might even be smaller than that. I have a picture of it, but it's hard to tell exactly how big it is. The whole thing is leaded glass, and then there'll be just this one little window of that leaded glass that's unleaded so that the x-rays can come through.
Okay.
So it'll look the same, just made up, what its makeup is unleaded glass as opposed to leaded glass. Yeah.
And that's the break that's at the bottom?
Yes. Yep. So that's that break at the bottom where the red is streaming out. That's indicating where the unleaded glass is. Okay, and there are some other parts, like if you look at the slide on 7, you'll see down below it says tube window, aluminum disc, lead collimator, blah, blah, blah. We're not going to learn about those yet. We're going to learn about those maybe next week, I think, if I remember the PowerPoints right. So there's a few more parts to learn, but I really wanted you to be able to visualize what we just talked about, because now I'm going to talk about the generation of it. And I just feel like it will be easier if you have a picture in your head. And so when I first started teaching this and I got the PowerPoint from the previous person, it just went right into the generation. And so I kept describing the parts, but I had no slides to describe the parts. So I was like, I have to have them at least visualize it. So tell me if that helps. Let me know, because I feel like it's nice to see an action in your mind. You have something to kind of think about when you're trying to learn the steps. Okay, so how are x-rays produced? If we go to slide 8, when the basic concept is when we have an electron flying across a chasm and it hits something really hard, really fast, things fly off, and those things are x-rays. So for a visual, you can think about a car crash. So if a car goes speeding down the road and it hits a brick wall, pieces of the car are going to fly off. And so it's just a simple concept to think about the actions of an electron. So okay, if we go to slide 9, conditions necessary for x-ray production. We basically have distilled this into 4 simple steps. Generation of electrons. So we got to get the electrons somehow. We need that. Production of high-speed electrons. The electrons have to move fast really fast in order to get x-rays. We want to focus them. We don't want them just going willy-nilly anywhere. We want them focused toward that tungsten target that we want them to hit. And then we need them to stop on something. So they have to stop on something that's going to be the right kind of material and the right element to stop it and then cause this reaction. So those are the 4 things. Generation, they have to be high speed. You have to focus them in the area, in the direction you want them, and then you got to get them stopped real fast. So those are the 4 things. So to elaborate a little bit more for number 1, so the generation of electrons, the machine in the room is plugged into the wall. And that's where you get the miracle energy. So it's just plugged into a 110 and maybe it's a 220. I think it's a 110. And this current goes into the machine and electricity starts heating up that coil. So that's where you're getting your energy from. So electrical current heats the cathode. So what's on the cathode side? Focusing that. Tungsten filament. So the current heats up that filament. The current from the electricity coming out of the wall, just your good old plug, that electricity has heated up the filament. That heat, it gets so hot that electrons in the valences of the tungsten atoms, so if you visualize like trillions of tungsten atoms, the electrons start getting agitated and literally boil away from those valences. So you get this concentration of just a cloud of electrons, basically, from the heat, because that tungsten coil gets so hot, it agitates them and they start decoupling from their atom, from those valences that we were talking about when we first were talking about the parts of an atom. So separation of electrons from the tungsten filament. The process is called thermionic emission. So they're emitting off of the atom, and it's because of a thermal reaction. It's because they're getting hot. So thermionic reaction, thermionic emission. And there's a test question on that. They'll say, what's it called? What's the process called when electrons boil off of the tungsten filament? And multiple choice, one of your answers is thermionic emission. Electron cloud is formed, and this whole process, so when you go into the room and you look at the control panel, we'll study the control panel a little bit better, but when you look at it, you'll see where you can change the kVp, which is kilovolt peak, you can change it from 70 to 60. So you can change that. We never touch it. We just leave it at 70, but you can theoretically change it. And then down on the bottom of the control panel, outside of the X-ray room, it's just stamped on there 7 MA. And MA stands for milliamperage, which is what the power setting that controls this process that we're talking about right now. So all you really have to know, you don't have to know much more like, I don't understand what milliamperage and all this kind of stuff. All you have to know and memorize is that milliamperage, and we just shorten it to MA because it's easier to say, controls this first process of generating available electrons. It's controlled by the milliamperage. And that is set. You can't change that. It's 7. If you go around and look at all the rooms, it says 7 MA. Can't do a darn thing about it. So just knowing that amperage is what controls this process is all you need to know for a test question. Okay. Any questions so far?
The milliamperage control.
Milliamperage controls the generating ability of electrons, or the generation of electrons. It controls the heating up of the tungsten filament and the fact that we even have electrons available, that whole process. And we do talk about an extra step I think it's next week or the week after, which kind of clarifies a little bit more about why MA controls this part of it, but we don't go too deep. But yeah, MA basically controls the energy needed to generate electrons. I'm trying to think of like the nicest way to say it. What's that? And our machines are. Now, I don't know about other machines. You could go into an office that has an ancient X-ray tube head, and literally the old ones you could adjust MA, but they don't really make them that way anymore. They just set them at what's a pretty good setting and everyone's happy. But if you went to an older office, or maybe they just simply had older equipment, it's possible you could adjust it, but usually they've set it at something and nobody touches it. But ours is set at 7. That will not be a test question. I'm not going to ask you what our MA is set at though. Yeah,
Did you also say that the MA controls the heating up of the tungsten filament?
it does. Yes, it controls that whole process. Yes. Okay, so, slide 11. So this is just showing you the electron cloud. So that filament heats up and all those electrons pop off, boil off, and they just hover around the filament. So right now they're just available for the next step. They're not doing anything other than just hovering around this filament. And that happens, you turn on the machine and the electricity starts flowing and the filament heats up and electrons become available. So that's just sort of in that state for until the next steps happen. And I just throw this in there as sort of a reminder. Again, there's nothing in this slide particularly that you need to memorize. I'm just trying to remind you that even though we're talking about solid things that you can see, this is all happening on an atomic level. Does that make sense? Is that right? It's all happening on a tiny, tiny, tiny level. So this, even though it's a solid metal filament that you could pick up and look at, the electrons are becoming available on this very tiny atom level of the metal. So that's just to remind you that that's where this process is occurring. Other than that, this slide you don't have to memorize. There's letters and numbers and valences, and I don't want that to make you think you have to memorize anything there. Okay, so slide number 13. So the second step, number 2, production of high-speed electrons. So there's two kind of, the electricity from the wall kind of splits off, and there's two sort of things that we talk about. We talk about MA, which I already mentioned, and then we talk about KVP, the kilovolt peak. And so those, and we'll talk about why that happens in another lesson. But basically those two things control different aspects. So we know that MA, it controls the generation of the electrons, but now we have those electrons ready to go, but we need to get them to be like high speed moving electrons. So we need something to like initiate that process. And that process is initiated by KVP, which is kilovolt peak. So again, just like MA, we don't have to go into the major reasons, the differences between the two or what are, because that's all like a different science that we just don't need to know about. But what you do need to know is in order to get high speed electrons, it's going to be controlled by KVP. That's just like you want to know that MA controls the generation of the electrons. KVP, kilovolt peak, is going to create the electrons to be a high-speed moving electrons. So it's controlled by KVP, kilovolt peak. So those boiled off electrons, because opposites attract, right? The cathode is, what side is it? Negative or positive? Negative. Anode is positive. And because opposites attract, that's one reason why they're just going to start heading off in one direction. In that world, like charges repel, opposite charges attract. So there's this gap between the filament and the tungsten target that's embedded in the copper, and it's really tiny. It's only like 1 to 3 centimeters. I guess it depends on how big your X-ray machine is. But it's just a small gap that those electrons need to be sent over quickly to the other side, to that anode. So electrons always move in one direction, always, always, always. They're moving from the cathode to the anode, always from negative to positive, cathode to the anode. So we got to have a production of high-speed electrons, and that's where our KVP comes in. Number 3, so slide 14, focusing the electrons is pretty easy concept. That focusing cup, the purple image on the picture that we're filling out, it is made of a certain material. I don't even think I test you guys on it. It starts with an M and it's hard to say. And oh, maybe it's in my notes. Is it in my notes? I want to say like mellum something. Anyways, it's in the textbook. I don't test you on it. I just want you to know that it is a focusing cup. So it's gonna, that electron cloud is gonna be hovering in the kind of concavity. And then when that high voltage gets initiated, the shape and the way it's designed helps to focus those electrons. They're going to move across anyways because negative, positive, that it kind of calls them over, but it helps to keep them kind of funneled in so that they really head over to the anode. You just otherwise they might kind of fly over there and fly over there, but you really want the vast majority of them to fly over and hit the anode. So that's the purpose of the focusing cup. And in the picture, the yellow piece that's not the part that's highlighted that says like charges repel, but in the actual picture, the little yellow rectangle, that is the tungsten target, just to reiterate that. It's embedded in the copper stem, and that's the tungsten target. So that's where all the electrons are the ones that we want to fly over and generate radiation. Okay, I have a little animation there. And then you can't see it. Nobody can appreciate it. Okay, number 4, stoppage of electrons. So we're almost done. We've generated them. Now we know how to get them to move high speed. We know how to focus them. And now we just need them to do it and then hit something. And then our reaction's going to occur. So electrons hit the hard, solid anode, which is positive, and it hits that anode and it stops those electrons abruptly, and a lot of kinetic energy is produced. Now, that kinetic energy is almost all heat, 99% heat. So that's a test question. Keep that filed away in your brain. So when this whole thing happens, it's very inefficient, really, because 99% of it is heat that just gets absorbed. Just it's not useful, it's not used for X-rays, just gets absorbed as heat. But 1% of that kinetic reaction becomes radiation. And that's what we want, is that we're going to harness those photons and try to make what comes out of that 1% as useful as we possibly can. And we'll talk more about some of the things that are set up in the machine to help make those more useful. But so the efficacy of X-rays production is pretty low when those electrons fly across from the cathode to the anode. They hit that tungsten target, bust apart. We get a lot of heat and 1% radiation, X-rays. Okay. There's a picture. Next slide, 16. That's a picture of, I wish there was something next to it, like a pencil or something, because it's kind of hard to gauge. There is a video embedded in the PowerPoint, and I think there's a guy talking about he has one, I think, and he's pointing to it so you can get a better, but it's small. It's not real big. Of course, if you have a bigger X-ray unit, it's probably a little bit bigger. It probably depends on, but you can see the copper. It looks copper, and you can't really see it because it's embedded in it. But where the copper is slanted inside the glass, that's where the tungsten target's going to be. And then what the metal part across from the copper, that's the focusing cup. You just can't see the concavity, and you can't see the filament because we're just looking at it from the side. But if you did a cross section of it, you would see those parts. Okay, so I really like the second video. So the first video, so now I'm on slide 17. The first video in green, large green letters, that's like just like a sciencey guy taking it apart, talking about it. He says things that are sort of not really necessary for you guys to learn, but it's interesting because he kind of shows a few parts. So I would encourage you to watch it, but don't stress out about knowing everything that he said. The second one, though, the second video, it's short and it just says everything that we just talked about in a really cute little animation. And so if you're a very visual learner and you just like to see things kind of cartoonized, that's a great video. I was going to play it for us, but I shall not. But I would recommend you guys watch that on your own because it does just basically says what we just talked about, but just in a nice little concise way. Okay, slide 18. This is just, again, it's showing the summary of the whole process. We have A is the focusing cup and the initial generation of the electron cloud. What do we call it when electrons boil off of the tungsten filament? Thermionic emission. Yep. B is showing them now they're high speed electrons. They're flying across over to, what are they going to hit? The tungsten target. Good job, you guys. And then when they hit that tungsten target, that's when X-rays are produced. So it's just showing it in a nice, concise. Yeah.
Is the red showing the 99% coming off?
The red is probably showing the 1% of X-rays. So yeah, it looks like a ton but when we talk about it as being 99% heat and 1% X-rays, but that's what they kind of want to draw your attention to is now X-rays are produced. So that's probably that is focusing on the 1% as opposed to the 99. Okay, so we'll let that kind of simmer for a minute. Let's see. I want to talk about, am I at that? I'm more than halfway. Let's just take like 5 minutes and let's just kind of digest that for a minute. I'm going to pass out, so you can get up, stretch, take a break, go to the bathroom. Probably not enough time to get a coffee, but just take 5 minutes and I'm going to pass this little worksheet out while you guys take a break and we'll is this recording? Where's the volume? Come on. That's 100%. Okay, now I have to figure out volume. What is it's not ever this complicated. It usually everything always just works. Okay, my volume's up. Is there like I was gonna say, where's the YouTube volume? There we go. Okay, that's the problem.
So some people less astute than the average X-ray student have wondered where X-rays come from. Maybe they're created by magical wizards. Maybe they're harvested from unicorns. Maybe X-rays aren't real at all. Obviously, you understand that X-rays are real, and this lesson is about the main principles of X-ray production. X-rays are real, and they have to be created in a very specific way. There's really 3 requirements of X-ray production: a source of electrons, a means of rapidly accelerating or energizing those electrons, and finally a means of rapidly decelerating or de-energizing those electrons. If any of these requirements are missing, X-rays will not be produced. In radiography, all 3 steps of X-ray production take place inside of the X-ray tube. Electrons are produced in the X-ray tube at the cathode filament. The specific process is called thermionic emission, which is the release of electrons, ions, in response to heat. And so it makes sense that it's called thermionic emission. A current running through the filament causes it to become extremely hot, so hot that electrons are actually dissociated from the metal and form an electron cloud around the filament. This is kind of like the filament in an incandescent light bulb. A current running through the light filament creates heat, which creates the light. In an X-ray tube, the filament gets so hot, it actually creates free electrons. The cloud of electrons doesn't do us much good. So what happens next? That's where the unicorns come in. Not really, but the second step of X-ray production is accelerating these electrons, which gives them extremely high kinetic energy. This is accomplished by an electric voltage that we call kilovoltage potential, or better known as kVp. The kVp creates a strong negative charge in the filament that forces the electrons across the X-ray tube. This makes sense since opposites attract. The electrons are repelled by the negatively charged cathode and attracted to the positively charged anode. The last step in X-ray production is decelerating the electrons. These highly energetic electrons slam into the anode of the X-ray tube, and in the process of decelerating, they actually release their energy as heat and, more importantly, as X-rays. The number of X-rays and the energy of X-rays are actually controlled by you, the technologist, using the MA and the KVP. Increasing the MA, or the tube current, increases the number of electrons produced in the X-ray tube. Increasing the number of electrons increases the number of X-ray photons. And this is the idea of intensity. The effect of KVP is slightly different. Increasing KVP, which is the tube potential, increases the energy of the electrons in the X-ray tube, and increasing the electron energy actually results in increased X-ray energy. So that makes sense. In summary, X-rays are not produced by magic or by unicorns. X-ray production requires three basic things: a source of electrons through thermionic emission, a means of accelerating those electrons, that's the KVP, and a means of decelerating the electrons, which is what happens when the electrons slam into the anode. MA is used to control the number of X-rays, and KVP is used to control the energy of those X-rays.
Now that last part that he talked about, the MA and the KVP, that actually is totally valid to what we're going to talk about in another unit. So you can file that part away for later. The only thing he said that does not apply to us at all is that we can't control MA. So like I mentioned, it used to be you could control the milliamperage on some older units, but our units don't let you control it. But the part about it generating more electrons or less depending on the MA, and then the power associated with the KVP, it's totally stuff we're going to cover. So that will become more useful. But for the moment, you can kind of stop it at maybe the 2-minute mark, and that's the stuff that applies to today. But I like the way, yeah, I like that video. It's nice and straight to the point, which I like. Okay. Let me get this to the Bremsstrahlung and characteristic. So now we know the overall process is that we know basically what happens when we have the available electrons, we have the voltage of power that makes them fly over to the anode, we generate X-rays. There are different kinds of X-rays that can be generated. Ultimately, they have to do with power. Some are going to have be more powerful. Their wavelength and frequencies are going to be different. And we'll talk about what that is in just a second. So that probably should have that slide here before I talk about it. And that's a mental note for next year, but we'll get to what makes them weaker and stronger in a minute. But Bremsstrahlung and characteristic are just basically two different ways that X-rays can be generated. One is very consistent, and it kind of generates a consistent, similar strength X-ray. The other one is a little bit more willy-nilly, and it's sort of, some of them might be weak, some of them might be strong. It's kind of a little bit more inconsistent. So Bremsstrahlung is the first one we're going to talk about, and that's the one that's a little bit more inconsistent. And the reason why it's more inconsistent is because we have to zoom back down to the level of a tungsten atom. We have to go back down to that size again and think about what the electrons are actually doing when they come in contact with a tungsten atom. So the electrons that are flying across that little gap from the cathode to the anode, those are called the bombarding electrons. We call them bombarding electrons because what are they going to do? They're going to bombard. They're going to bombard the tungsten target. So when they come to the tungsten target and they come in contact with it on an I keep wanting to say atomic level. Is that right? Am I using the right word? Just, do you know what I mean by that? Like, we're zooming down to the atom, but I feel like it sounds like atomic bomb or something. So I feel like it's not the right word, but on a microscopic level, when we're looking at the atoms of the tungsten, that bombarding electron is going to come into that atom, and there's all of those valences. There's those orbiting electrons, and it flies in and it doesn't actually come in contact with any other electron in a valence. It just makes its way through somehow and it gets really close to the nucleus. And for one reason or another, instead of like crashing into the nucleus, it makes a sudden turn. And that act of making a sudden turn releases energy and it releases an X-ray photon. So and beyond that, there's probably much more that could be said about it, but we're gonna leave it there. When that bombarding electron flies in and comes in contact with a tungsten atom, it manages to bypass all the electrons in all of the orbiting valences, and it gets really close to the center, the nucleus. But before it hits that nucleus, it goes whoop, and it makes a sharp turn, and it releases some energy because of that motion, some kinetic, some energy, and what that energy is an X-ray photon. Now, it could do that in a number of different ways. It could actually move in different areas of the atom. And when that happens, some might be really strong, like strong X-rays is the only way I want to say it right now. They might be really strong, kind of good, useful X-rays. It might do that same motion where it kind of veers off, but in a different part in an outer ring, and then it's going to put off a weaker X-ray. So Bremsstrahlung is a little bit willy-nilly because sometimes they're good, strong X-rays. Sometimes they're not so useful, weaker X-rays. So the big thing to remember about Bremsstrahlung is basically that motion of flying in, veering off, and then that motion creates these inconsistent strength X-ray photons. So if we go to the next slide, we could just have a little animation of it. If it works, please work. So there's the bombarding X-ray, it rotates around the nucleus, and then an X-ray photon comes off. Let's watch it again. In comes the bombarding electron, moves around the nucleus, out comes an X-ray photon. Doesn't actually knock out anything. Any of those other electrons don't get knocked out. Yeah.
So are you saying when it knocks off like in shell 2 or shell 3, it's gonna be a stronger X-ray? When it knocks off like shell 5, will be a weaker one?
If with that process, yes. If it knocks off an outer electron, it's gonna generally be weaker. The closer in, because those are bound stronger, and so they have more energy potential to release. They're gonna create a higher powered photon, radiation, X-ray photon. Yeah, good question. Good. And that is one way to just kind of sum it up in your head. So the next one though, so that's Bremsstrahlung. The next one on the next slide, 22, is characteristic. So characteristic is going to work very differently because instead of this just veering motion, swerving motion of the electrons, characteristic knocks electrons out. So it knocks electrons out of shells, out of these orbiting shells or the valence. And so the bombarding electron comes in, and if it were to knock out K shell, which is the closest one to the nucleus, if it was to knock out that one, it ejects that electron. We now have an ion. That's we have like an ion pair because now we have it's not neutral anymore. That atom is no longer neutral, and we have this negatively charged electron just out in the world. But so it knocks it out, and then because the nature of atoms want to be stable and they want to be neutral, there's a movement of all of the electrons in all the other valences to move inward toward the nucleus and satisfy that maximum number of electrons that each valence holds. So all of those electrons move in, and that motion of it, that whole process creates characteristic radiation. So the process releases energy, releases an X-ray photon. And the difference between characteristic and Bremsstrahlung is because this is much more predictable. Like if all of the X-rays move in, that valence carries like this binding power and this energy will be released. It kind of helps to know consistently the power of the X-ray photon that's going to be produced. So generally speaking, if a machine is set to 70 kVp, which is necessary to make an electron strong enough to knock out a K-shell electron, then you know that characteristic radiation is going to be produced, that kind of and that's not to say that other weaker ones, it's not to say that there can't be other things happening, but you know consistently you're going to get stronger, consistent X-ray photons with characteristic radiation. So some of the notes here, sometimes I don't always read my notes from year to year. So, but I do see that I highlighted K-shell electron. So the bombarding electron is done. It's used all of its energy, and it can't go in. So that's another difference. That with Bremsstrahlung, if we take a step back and think about Bremsstrahlung, that bombarding electron that came in and just swerved, it could go on to a different atom of tungsten and do the similar thing. But it would probably produce even weaker still another X-ray photon, because at that point some of its energy, it's done, it's gone in one area, and so now it's going to go in another area, and it's just going to kind of do it until it's used up all of its energy. So it's not very efficient, it's not very effective to get really strong radiation. But characteristic, that one electron comes in, that bombarding electron, and it just completely slams in with another electron, and it knocks it out, and then it's gone. It's used up. It kind of just, that's the end of its purpose for that one interaction. So if we look at the next slide, the little animation here, it just shows, these are so short, it shows it coming in, knocking out an electron, and then things move forward. That one doesn't show it. I don't feel like it shows it as good as, because you don't see all the kind of movement that would have to take place, because all of they would all want to satisfy the next valence, but at least it gives you the overall difference between Bremsstrahlung and characteristic. Characteristic knocks out an electron from a shell. Bremsstrahlung swerves around, changes direction. Do you guys have questions about that? Sometimes things just have to sit for a minute. Yeah.
With the characteristic, then does it always knock out from the K shell?
Mm-hmm. I want to say no, because we do end up with different strengths of X-ray photons. So the most useful ones and the ones that we sort of focus on, because they're the ones that oftentimes have the energy to get out of the machine altogether, because there are things, and that we talk about the way they build the unit, there are filters that filter out weaker X-ray photons. So that tells me that there are some photons, X-ray photons, that are produced that are not so useful and they're weaker, and then some are stronger. So I think the answer is it doesn't always do a K-shell. It could do a different one. I'm not going to test you on that theory just because I don't feel like that's the main point that I want you guys to know. I do want you to know that there are variation strengths of X-rays. Some are weak and some are strong. Some make a better image, some make more of a fuzzy image. That part I do want you guys to know. Yeah.
So are you saying it's just like by chance when we take an X-ray, we're gonna get either characteristic or Bremsstrahlung?
Yeah, well, ours are all set at 70. So I do think that we used to say when I first got this course, the notes said we always only make characteristic. But then I kind of dug into some of it because I had that question because people would ask me, they're like, so do we only make characteristic? I'm like, well, is it impossible to make Bremsstrahlung? So I dug into it and it doesn't feel like it's crystal clear, like 100% yes, only this. But I would lean to that. Like if you just want to settle it in your mind, it's probably characteristic that's being produced. All of our machines are set to 70 kVp, so that gives us the good strong voltage to knock out a center, a K-shell electron. But again, I'm not gonna ask you about that. Like, what kind of, that used to actually be a test question. What kind of X-rays do we produce in our lab? And the correct answer used to was characteristic. But I always felt like, well, maybe some Bremsstrahlung is happening. How do we know for sure? We're not electrons flying around the atoms. So I took that question out because I didn't like it. But it's a good thing. You know, you think about it, you're like, well, what's it producing? But I do think the answer is predominantly characteristic radiation. Okay, so this is that same slide from before where I was talking about, think about this metal as not just a solid piece of metal in the form of a target or a filament, but also atoms, you know, trillions of tungsten atoms. So this is, we're highlighting here the K shell, the innermost shell. There's only 2 electrons, and approximate binding energy is keV. And so that's where that kVp, the kilovolt power, relates to the binding power. So that's why when it knocks out an electron out of the K shell, it creates this high, this you know, when I speak it out loud, it kind of sounds to me more like it's only considered characteristic when it hits a K shell. Are you guys feeling that? Do you feel like that makes sense? Like when it hits the K shell? Because the more I say it, because I was thinking that characteristic could happen on different levels, different shells, but I think that perhaps actually, especially with this, you can only get that high powered radiation X-ray photon when you have a 70 kVp. So it's a process that needs that power. So if it doesn't have that power, then it's not going to create it. And like I said just a second ago, that is the power that our machines are set to. Okay. If you study that and it's murky, if it's a little muddy, we can revisit it. I always like to start out the next lecture, like Tuesdays are these harder lecture days. I always like to start them out with a little bit of like, what was muddy from last week? What are you still kind of struggling with? And so if you let that kind of simmer and you come back with a question, that's great. And sometimes I'll have a few like sample test questions at the beginning of the class too. Okay, so we're going to go on. This is pretty easy concept. I don't go deep into particulate radiation at all. We don't need to know about it, other than we just want to know the difference between particulate radiation and electromagnetic radiation. Electromagnetic radiation is pretty much the radiation that we just swim in. We just live in it. Like if we could see it, it's everywhere. It's you know, our cell phones, our microwaves, the X-ray machines, but there's different TVs, radios, everything. So, but there's different wavelengths and frequencies, and that matters to our health. So the different, you know, the higher the frequency, the shorter the wavelength, the more intense and the more biological damage really can take place. So that's the main difference between particulate radiation and electromagnetic is particulate is a specific kind of radiation that we're not, for one, dealing with when we make X-rays, and but for two, it carries a charge. So particulate radiation is very different from electromagnetic because it literally has mass and it carries a charge. So it's particulate radiation. They're tiny particles of matter. They possess mass. They travel in a straight line at high speeds. The only test question and that's why it's highlighted, that I ask you about particulate is for you to identify the difference between it and electromagnetic in relation to the fact that it has mass and charge. So if you remember that particulate radiation has mass and charge, really that's all you have to remember. So I don't ask you, there's other things down here you know, it's a little bit more kind of, there's a few more things for those of you that just, maybe you love this kind of science and you're like, I want to know more things. Well, there's a few more things, but really the only thing I test you guys on is the difference there, and the particulate has mass and charge. The cathode ray, which is what Renkin was originally playing with, that is particulate radiation. But then he was, because of whatever he was manipulating and the differences in his lab, he ended up producing X-rays. But that was the cathode ray, beta particles, things like that are particulate radiation. So electromagnetic radiation has no mass and no charge. And that's basically what we're dealing with. That's what X-rays are. And that's what we're dealing with. And we'll look at the spectrum here. So electromagnetic radiation, it can be defined as, sometimes they talk about it, it can be observed as like an energy packet. So sometimes it can be observed as like a particle, but then it can also just be observed as in a wave. So one way that somebody described it is like a surfer on a wave, like the wave changes shape, but the surfer is on the wave moving with it. So the surfer doesn't look like they're going like this. The surfer looks like they're going straight, but the wave is changing around them. So depending on how you look at electromagnetic radiation, you can observe it differently. So it's a little bit kind of like, kind of crazy in the brain, but that's the best way I can kind of think about it, is like a surfer on a wave. Electromagnetic radiation are believed to move through space as both a particle and a wave. Two concepts. The particle concept characterizes electromagnetic radiation as discrete bundles of energy called photons. So after the electrons, so sometimes this terminology is very easy to mix up. After those electrons have bombarded the tungsten target, they're no longer electrons. What we have now is we have X-ray photons. So that's the little packet of energy, an X-ray photon. Okay, so the wave concept. So a wave, we have a couple things that we want to think about when it comes to the wave concept. We want to think about the wave length, which is going to be the distance between one peak to another. So you could have a really long wavelength, or you could have a really short wavelength. And so it's just the distance from one peak, sorry, this is kind of in the way, distance from one peak to the other. So these are a lot closer. And then the other term that you want to know is frequency. So if we measure, if I had this whole board open and I could just continue this longer wavelength, if I measured 3 feet, and within that 3 feet, I counted up how many peaks there were, the peaks that had, the measurement that had fewer peaks has lower frequency. The peaks where there's like 15 peaks in that same measurement of space has a higher frequency. So if we take just a chunk, a length of that wavelength, the one that has more peaks is high frequency. The one that has fewer peaks is low frequency.
Can you repeat what you said, the wavelength was?
Yeah. So the wavelength, so depending on if the peaks are close together or far apart, that part doesn't matter with wavelength, but it's just the distance. If they're shorter, it's a closer wavelength or a short wavelength. If they're longer, so we're measuring from one peak to the next, so just 1 to 1. If they're farther apart, it's a long wavelength. If they're closer together, it's a short wavelength. You're welcome. Yeah.
When you're talking about the 2 types of radiation, like how do you know which one you have? Like, do we just get it by chance, or?
It's the way it's generated. So that goes back to that would travel back into a lab with scientists doing stuff. they do something very different to get particulate radiation as opposed to what we're doing to generate electromagnetic radiation. So it's a part of that process. So that whole process that we're talking about where we need electrons, they need to be high speed, the whole thing, those are all necessary components for just electromagnetic radiation. And they're going to follow a whole different path to get particulate radiation. And thankfully, we don't have to memorize that. We don't got to know it, but it's going to be a whole different set of requirements. So, but that's a great question. Okay, so wavelength frequency. So this slide here, so basically what we want to know about the difference between long and short wavelength and frequency, basically what we want to know is when it comes to the radiation that we are creating, a wavelength that is short, so close together, all these wavelengths are really close together, it's going to make an X-ray photon that penetrates better. It's going to make an X-ray photon that has higher energy. It's going to make an X-ray photon, therefore, with a higher frequency. I'm like standing in front of, let me use my mouse, with a higher frequency, just because all those peaks are closer together. So it's a short wavelength, high frequency. Short wavelength, high frequency. And then that means, in layman's terms, it's going to go through things better. So it's just gonna go through the teeth better. It's gonna go through the cheek better. It's gonna go through the bone better. So we want X-ray photons that have short wavelengths, high frequency. On the other side, just the opposite, if it's a long wavelength, it's going to have a lower ability to penetrate. It's going to have lower overall energy. It's going to have a lower overall frequency, and therefore it's just going to absorb. So it's going to absorb into the cheek. And if an X-ray photon absorbs into the cheek, it's done nothing but damage the patient biologically. Not so that they'll die, but on a cellular level, there's a teeny tiny itsy bitsy bit of biological damage. So we want to minimize the amount of useless low power X-ray photons. Can we eliminate them 100%? No, we just can't. But we are amazing creatures that can recover from a teeny tiny little bit of cellular damage. It's a balance to talk to you guys about it. Because yes, there is real damage. Remember what I said, it's a risk benefit analysis. Yes, something happens on a cellular level. Do you want to just bombard yourself with it endlessly? No. But do you need it for some other really important information? And does your body generate and heal? Yes. So it's a balance there.
So, I have a question.
Yes.
Short length then penetrates better like hard tissue.
Yes, yes, everything, teeth, bones. If it's a short wavelength, high frequency, it's just going to penetrate better.
But it doesn't get absorbed on soft tissue.
Yeah, it'll go right through the soft tissue. Yeah, and what we want is we want them to get as far through and make it to the sensor. However, we absolutely know that they don't all get to the sensor, and that's why we have the grays, the opaque, radiolucent grays. And so it doesn't make sense for them all to get to the sensor, but we want them all to do the best job they possibly can, because it actually makes the image clearer and better, like ultimately what you were talking about. So when they all do their best job, then the picture looks better. Okay. If I have been paused this whole time, I will be mad at myself. No, I think it's recording. Okay. All right, so this is just a visual. Another thing that we talk a little bit more about ionizing, but you notice how on this side we have the light bulb sort of in the middle, and on the non-ionizing form, see how the wavelength is all kind of long and low, the frequency is low and the wavelength is long, and it's all non-ionizing. So AM radio, FM radio and TV, cell phones, radar, TV remote, all the things that we do wirelessly, Bluetooth, although I'm like, you'll learn about me, I'm a little bit of a skeptic of things, and I'm like, You're telling me that a Bluetooth earbud, all day long in my ear is good for me, but technically it's on this side. But I don't know, maybe more research in a few years we'll be like, oopsies, we didn't know that. That's bad for us. But anyway, but for this picture, we have on this side the non-ionizing radiation. And then you'll notice on the other side where there's ultraviolet, the sun, the sun burns, right? Some people can get, sunburn badly. Some people will blister and peel if you're out too long. So sun causes some cellular damage. So you can think of that on the other side, that's where we start to get some of that higher frequency, shorter wavelength. Then we have X-rays and then radioactive elements, gamma rays and things like that. It gets far more damaging much faster. There are still some purposes for it in specific things, but in general, it's not something you just want to be around. And this is just another way of seeing it. It talks about the wavelengths. There's some numbers associated. I don't test you on any of those numbers. We don't go there at all, but it's just another way to visualize the wavelengths, the different things that are associated with those wavelengths. And I don't really test you on the wavelength in general, but it's just a good I feel like it's a good visual to kind of think about it. Okay, so now we're going to wrap it up here. I do want to spend, I'm going to go over these last few slides, and then I do want to spend just a few minutes with you guys talking in groups about the handout that I gave you. It asks you to summarize the production of X-rays, and then the second question says, what does it say about catnap? The second question says, describe how catnap can help you remember the flow of electrons in the X-ray tube head. CatNap is referring to, and this is in your textbook, so if anyone has a textbook and has been reading it, they might have seen a little picture. But CatNap is a way for you to remember the C is for cathode, C is for cat, cathodes are negative, cats like to take naps. So I wanted you guys might not have known, people like, what is catnap? So I thought I would tell you about it first, let it marinate, and then you can write it down. And if that helps you, and then you just know automatically, if the cat takes a nap and the cathode is negative, then obviously that makes the anode positive. Because you do get I asked you a question about that. And you get it again at the end of the semester when we have the comprehensive. So it'll come up again at the end of the semester. So you always have to remember that. Okay, let's go over these last few slides. Interaction with matter. So how do X-rays interact with matter? The penetrating power. X-rays can penetrate liquids, solid, gases. The composition of the substance determines whether the X-rays penetrate, pass through, or get absorbed. And that's really important to know. So basically, when we are talking about cheek cells, when we're talking about bone cells, when we're talking about nerve cells, when we're talking about amalgam metal, an amalgamation of many different metals. But when we talk about an amalgam filling, whether or not it's very dense or not so dense, is going to determine how well the X-ray is penetrated. Absorption. X-rays are absorbed by matter. The absorption depends on the atomic structure. So that's where the atomic number comes in. But again, like I said in the very beginning, I don't focus too much on that, but it does influence it. And the matter and the wavelength of the X-ray. So if you have something, that's why the little glass tube is leaded glass. Lead has a very high atomic number, and it's just going to absorb especially the weak, low energy X-ray photons. So that's absorption. If you have something that's very dense, has a high atomic number, and then you have especially a weaker X-ray photon, but really any X-ray photon is going to get absorbed by lead. It's gonna absorb it. Ionization capability. X-rays interact with material they penetrate and cause ionization. So whether or not we're talking about a tungsten atom or a cheek cell, if an electron gets knocked out, if the cell gets somehow damaged, we're going to create ionization, which causes cellular damage. So that process, and we talk a little bit more about that when we talk about the biology part, which helps clarify that. But the whole process causes ionization. Fluorescence capability. This one, I don't know. It's here, but I don't really ask very much. X-rays can cause certain substances to fluoresce or emit radiation in longer wavelengths. That is what Renkin noticed in his lab. So something was glowing, and that is what initially led him to realize he wasn't just working with a cathode ray. It was some other kind of ray. And by the way, that's why they call it an X-ray. It's the unknown. X is the unknown, right? It's the unknown ray. So that's where the X-ray comes from, in case you were wondering about that. Effect on receptors. X-rays can produce an image on a receptor. So all of those electrons are not electrons, excuse me. All of those photons, the ones that hit the sensor in different varying amounts, react with that sensor and create different amount of pixels. And we talk about that in another unit too, but that's how the image ends up on your computer eventually. Effect on living tissue. X-rays cause biological damage in living cells. So that is a true statement. There is some level of biological damage. Yeah.
With those terms, like on a test, we just ask us like what is absorption or what is kind of ionization capability?
Yeah, it's a little bit more of like the concept of that for that one with the penetrate, like how does it interact with matter? It's more like understanding it can go through it, it can be absorbed by it can cause changes, it can cause ionization. So it's a little bit more of like a concept understanding for that slide. So the question might be like trying to think of a specific question. But yeah, it'll probably ask something more about the density of material and penetrating power, and then the power of the X-ray photon to get through those different. So it's more about absorption, getting through, penetrating. So it's a little bit more of concept as opposed to like just memorizing a term, if that
Yeah.
makes sense. Okay. Properties. So almost last slide. The appearance of X-ray. So these are the properties of an X-ray. They're invisible. You can't see them. That's why the guy was joking about them not even being real, but they're invisible. They have no mass and no weight. So that different from particulate, no mass, no weight. There's no charge. They travel at the speed of light. Fast, 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 fast. Just like when we turn on the room light and the light source is there, and then the light becomes ambient and spreads out. X-rays do the same thing. Oh, that doesn't talk about that yet. Oh, well, it kind of does, the path of X-rays. Well, okay, let me go to the wavelength. So wavelength, X-rays travel in waves. They can either be, short wavelength, higher power, or a longer wavelength, lower power. And then the path of travel, X-rays travel in a straight line, but they can be deflected and they can scatter. And we'll talk about scatter, I think it's next week. But so that's what I was trying to say is just like when you turn on a light and the concentration of the light is in the bulb, but then it diffuses out. So light particles, light photons do the same thing. They move out sort of in a they spread out. So X-ray photons will do the exact same thing. So we try our best to control where they're going. We just want them to hit here. We don't want them to hit here. So, and we talk about all the different things that interact with the X-ray photons to help us get to that kind of nice dialed in location for the X-rays to hit. But just knowing they go in a straight line, but they sort of splay out, just like ambient light does the same thing. Focusing capability, X-rays cannot be focused to a point. They always diverge. Diverge was the word my brain was trying to get to. So X-ray photons, they go in a straight line, but they diverge. Just like a flashlight, strongest at the source of the flashlight, diverge and kind of spread out as you hold the flashlight, farther away. This says the same thing. Behave like light, spread over a distance like a beam of light. They're invisible, travel in a straight line, penetrate material that absorbs or reflects. They cause ionization. They can produce fluorescence in certain substances, differentially absorbed based on matter. So they will absorb differently depending on if it's dense or not as dense. And then they produce biological changes. So that's kind of a repeat of the earlier slide. It's just said a little bit like less words. I love questions. Questions are my favorite. Is Elf like not anyone here's generation movie, or are there any hardcore Elf lovers? I love that. That's like my favorite Christmas. Well, I don't know if it's my favorite Christmas movie, but it's pretty high up. Do you guys, yeah, okay. I always wonder, like, the older I get, I'm like, will I have anything to relate to these students about? Every generation comes in, you're younger, younger. Okay, so I know your questions, you're probably tired. Your brain's probably too tired for questions. So, but if you have them, please, you guys are asking great questions. But let's take just 5 minutes. Let's take 5 minutes, work together and answer that first one, kind of write down the process. And then write down a way that you can kind of help to remember that cat nap, cathode negative, anode positive. And if it's just repeating what I said, that's fine too. I just want you to kind of get it in your mind. And while you're doing that, I'm going to hand out the take-home quiz. This quiz does have to come back to me next Tuesday. Part sticks out, or you can go back toward those 4 steps. You want to get that PowerPoint. Let me look at my own. If I have them, I will bring them up. This helping so that I know that.
So I put cancels negative and it was in that more positive than your little questions, but. That's why it says. Anna. There you go.
Okay.
You could say all because so that's 99. Rate X-ray photons.
So when did it come out?
Well, the heat is it actually does get absorbed. It doesn't come out in the end. It actually gets absorbed.
Yeah.
This most that's mainly why it does a good job as perfect heat. So actually most of them are actually this target and then heat does absorb. Some heat probably does come off of it, but mostly the purpose is for it to get absorbed.
Oh, and that creates the.
Yeah, well, and then the X-ray, this is confusing because it does look like, oh, something wants to come out of here. But just, I wouldn't focus on that, except for the fact that it's on positive end. I wouldn't look at that so much, as much as this. Because this is where the X-rays. Here.
This is where it's taken.
Because this whole thing is all leaded glass, so no X-rays can come there at all. But then there's this little window of unleaded glass. And then the rest of it is that other metal casing is what you manipulate, so now I just boil and that's organics, it just produces a lot. So it's just the whole process, just.
Yeah.
So.
So then it's just 1%.
Just, well, because it's a percentage of, you know, how much, like, let's say it produces, you know, the numbers like 1%, 1% of a million, is still a lot.
Yeah.
And there is an exposure time, so when you like hit the button and it goes,
I think
that it's higher time, it's like, it's creating. The whole. So, yeah, so it might be only, so I know, like fractions of a second, or like a second and a half. That they are tracing access. So that for your 1%. So it's not enough to take the big stuff. So.
Yeah.
Yeah.
It's like very low. Yeah, got it. I've done no opinion. They're going and the last pool and we all those.
Sensor.
And the quiz is front and back, so don't miss the back side.
And then we get pushed. And it's separating all of them. And we then my own committee. And that creates a 1%. Which is the. And the page on each of the both, like both page, is all into reduce the extract and the columns. You want to go now. Now, the piece. And please see. Okay. Oh, so you're right. No, yeah, that's what I see. Yeah, they get to hear that one, and then they separate from the next batch. Right, you keep it like everyone they speak here. Oh, yes. Yes, so they get. That like they just. Really, it's like it's easier. It's just. Then it's big, it's years. So it's a boy, so it is once it. That's why you would they get sent on. And then this is. But it doesn't, it's just. Yeah. So I think. I was like. Oh, that. I was like. Everyone's ever. But then now the rest of the kind of. So much better needs space and sufficient. Which kind of. Yeah.
Okay. Do you guys need a few more minutes or? I hear, oh, it died down. It got quiet, so I thought maybe, but I don't want to cut you off before you're done. Maybe, let's see, we got maybe 2 more minutes and then we'll share out.
Yeah. So it almost, not that though. Yeah. It's still in the. Oh, it's all exactly. And then it's that, right? Price not why. It will use. Oh, really? Which kind of like sounds like. So, you know. And then. And we haven't really cracked. What? Yeah, as long as you know where you're headed, yeah. So, but I do think it's. Well, they're definitely like they're not. You're definitely towards my DNA class. But what if the boys was like, we're going to all of the courses there. Then not very, as long as it's here. Right, and then it's choose something like yours. I don't understand. I think it stays for that. Oh, yeah. I think, when things are, the oil around the surface, that passes through the teeth. Okay, other things in the electric about they can find little notes, the door, and it, whatever is on the definition, we have expected from the. Yeah, just like, so you. All the oil. So I want to think about that and go tell the end of the story. I think, but yeah. You know, right, I want, well, other people. This, and now I realize the best. And then on the inside, you have a sensor. There's currents and some of them will make it too sensitive. And so I didn't know. To make the big up, like the big. Although it's years and everything. That's the total story. But there are still a few more things. Yes, you are welcome. Yeah. So where are the? Yeah. So is it like a census process or is it like the? It's no, it's like a version, like I plug it in the wall and that's what just some of the. But you push it down in the little oil stab. But you have to have planned it. A battery, probably. Yeah. Probably battery. Yeah. It's a good question. Oh my god. So there's, I'm like concerned like getting the. Yeah, just that furnace that you plug it in and turn on, yeah, then the furnace is flowing on that. So it's it starts heating it up and then you start scanning. Oh, see.
So instead, I think what I'll do is, let's see, what time is it? We have 3 minutes. Really quickly, I want to just say, please, 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 please don't forget to do, in all the shuffle of papers and all the things that have to be done, write your name on the top and put it somewhere where you'll remember. You don't have to do it today. You can do it over the weekend, but it's due next Tuesday. It's due next Tuesday in the beginning of class. So just don't lose it. Because, and also you guys can do it together, but like I already told you, test yourself, like really do it as a quiz. And then if you need to change the answers and you just, you want to get 100% on it and you compare with someone else and you're like, oh shoot, I answered that wrong. Then change your answers, it's fine. But just test yourself with it. And then let's have, who wants to share what they wrote for the first question, thinking about the production of x-rays? Anybody brave? We've got 2 minutes. Just say it fast.
It's not but turning this, but like I have a little bit of a confusion in the with the thermal emission process.
Yeah.
So like you get the heat to produce the energy, right?
Yeah.
The electrons get released.
Yeah.
And then they, in that between the filament and from the cathode to the anode, that's where the boiling happens, right? Like
It happens on the cathode side.
that happens in the cathode, not probably. Okay, and then once they get boiled up, then they get shoot up over to the other side.
With that bolt, when you push the button and it goes beep, you've just given it a bolt, and that's what moves those electrons
Okay.
over.
So that get transferred, they fold it to the.
Yeah.
Okay, okay, and then they get to the constant
Target.
Yeah, and then when they hit that, they kind of.
Yeah, and then, so that whole, when they hit it, yeah, it creates that kinetic energy, which is mostly heat and 1% X-ray.
Yeah.
And like I was telling somebody else, when you push that button and the whole time, some beeps are really short, some are like beep and it's done. The ones that are like beep, I mean, it's like fixed forever. But that whole time that you're creating an X-ray the whole time, it's an exposure time. And so that whole time it's getting that voltage to push those electrons over to the tungsten part.
And you must hold the button until the
You
heat stops.
gotta hold the button. The R's are really obnoxious. If you do not hold that button, it's gonna error and then you're gonna be like, oh, and you have to reset it. And some of them don't like being reset. They're just funky. I don't know. We had the ones we had before the beep was short. We recently changed out a few. The beep was really short and they never errored. These ones error. So, okay. So that's it. We're at 9:50. I want you guys to have a break before your next class. So get up, move around, get a drink. I'm in my office today. If anyone needs me, has questions, pop in and you can ask me questions. Okay. Yes, here, let me stop the, yes, for sure.